Hello, I'm Scott Schuetter, the principal investigator for this project. I'm a principal engineer with Slipstream and will be presenting a short summary of this demonstration. First, a little background. Department of Defense facilities consume approximately 30 billion kWh annually. Lighting accounts for 18% of electricity use in commercial buildings, meaning that DoD facilities use a lot of lighting energy. LED retrofits can effectively reduce this end use. Lighting controls can increase the savings of LED retrofits. However, they aren't frequently included in retrofits of DoD facilities. The objective of this project was to demonstrate and accelerate the deployment of advanced lighting controls in Department of Defense facilities. We evaluated energy, demand, and utility cost savings. We also evaluated the light levels of the retrofit, ensuring they're in line with UFC recommendations. We quantified the installed cost and associated economics, as well as stakeholder satisfaction with the technology. Finally, we evaluated the cybersecurity of the system by ushering the system through the RMF process. The advanced lighting system evaluated within this project is the Cree SmartCast system. This system includes LED fixtures with efficacies of 130 lumens per watt, resulting in fixture powers ranging from 25 to 30 watts. It is available in form factors for most interior low bay applications. It's mainly applicable to office and associated spaces. It includes an integrated occupancy and photosensor that wirelessly communicate between fixtures and with dimming switches. The system therefore can reduce the lighting output during periods of sufficient daylight and turn off lights during periods of no occupancy. It also includes task tuning capabilities, thereby capping the power and lighting provided by the system to a value below the system's maximum. This is done to reduce the lighting in a space that would otherwise be overlit. Finally, the commissioning process is simplified, saving the associated time with programming the controls. The overall project's approach followed these steps. It started with site identification. We characterized the existing lighting system in each building. We installed monitoring equipment to capture the pre-retrofit performance. We implemented an occupant survey to understand pre-retrofit perceptions. And we managed the design and installation of the Cree SmartCast system. We then repeated the lighting characterization and occupant survey and continued gathering post-retrofit performance data, including installer feedback and cost information. We then analyzed impact of the retrofit and are currently finalizing our reporting of the project. We demonstrated the system at 2 Air National Guard bases, Truax Field in Madison, Wisconsin, and Selfridge near Detroit, Michigan. At Truax Field, we replaced the lighting in portions of one building, including open and private offices. The spaces had existing fluorescent fixtures with no automated controls. They also had significant daylighting availability, but no photosensor control. At Selfridge, we retrofit the lighting system in portions of 2 buildings, including open office, private office, conference rooms, and circulation spaces. The lighting system was similar, fluorescent fixtures with minimal automated controls. Plenty of daylight was available in the perimeter spaces, but there was minimal to none in large core open office areas. We calculated savings across multiple performance metrics. As you can see, the electric energy savings was significant, with an average of 2.5 kilowatt hours per square foot, or 69% of lighting energy. This equated to roughly proportional savings across peak demand, greenhouse gas emissions, and utility costs. Through analyzing the daily profiles across each space, we calculated that 48% of the energy savings was attributable to the switch to LEDs. The remaining was from the controls. Note that these proportions will be different in spaces with more variable occupancy or different daylight availability. The utility cost savings equated to between 22 cents and 55 cents a square foot, averaging 42 cents per square foot across all spaces. This led to a long, simple payback of 20 years. Upon reviewing the installed costs of our project, it was clear that they were higher than expected. This was driven by longer installation times, fixture densities, and higher fixture densities and higher contractor markups than we assumed. These may be functions of the relatively small sites that we analyzed, combined with the research nature of the project. There is good news, however, as trends indicate the cost of these systems is coming down. We found two other studies, one from the General Service Administration and one from the Department of Energy, that published costs much lower than our costs. If we were to use these costs in place, the economics of the system would be much improved, with paybacks approaching 8 years. The results of our occupant satisfaction survey have been overwhelmingly positive, even with the overall light levels generally being reduced. Here are the pre and post retrofit results when we asked how satisfied occupants were with their light levels. Before the retrofit, there was a wide range of satisfaction. In general, the open occupants couldn't quite agree on whether they liked or disliked, as expected since individual preferences vary and the lighting provided was uniform. In the private offices, the feedback was more positive. However, post-retrofit, the occupant satisfaction improved across the board, with a significant portion of extremely or somewhat satisfied respondents. The score was up from 2.5 to 1.6, with 1 being extremely satisfied and 5 being extremely dissatisfied. In conclusion, we found that savings are significant, but cost and cost effectiveness are challenging. Fortunately, this seems to be improving. A few qualitative lessons learned from our project. It's important to get facility staff and office manager buy-in. They're valuable resources throughout the retrofit process. Specifically, we found it useful to create a control matrix. This table outlined our assumptions regarding how each space's lighting would be controlled. The facility staff and office manager reviewed our assumptions and provided feedback based on their understanding of each space's needs. The feedback helped optimize the controls in each space and minimize subsequent complaints. We further found that photometric models are useful. However, ours weren't as accurate as they could have been. They would have been improved by more precisely modeling interior partitions and associated storage cabinets. Then confirming these light levels with spot measurements is always a good idea before adjusting task tuning set points accordingly. It is important to obtain buy-in from the occupants. This similarly involves educating them about benefits of the system and their operation. This can be done through simple brochures left at their tables or an email succinctly describing the new lighting system and its purpose. Finally, if you would like more information, please feel free to visit the link provided or contact me directly. Thanks so much.